Hi everyone, welcome to Mathemly. Welcome to the finale of our neural networks series. In our last video, we explored the dimension of time, learning how RNNs and LSTMs use memory to process sequences like text and speech. But as we conclude this journey, we have one final massive challenge to tackle: vision. How does a computer look at a grid of millions of colorful pixels and instantly recognize a cat, a face, or a stop sign? Up until now, we have handled data as lists of numbers like house features or word vectors. But images are different. They contain spatial patterns, textures, and shapes that are easily lost if you treat them like simple lists. Today, we are diving into convolutional neural networks or CNNs. These are the architectures that revolutionize the way machines see by mimicking the incredible complexity of the human visual cortex. Think about a standard feed-forward neural network. To process an image, we would have to flatten it, taking every row of pixels and lining them up into one giant long column of numbers. But here's the problem. When you flatten an image, you destroy all spatial relationships. A standard network doesn't know that pixel A was originally right next to pixel B. It loses the concept of up, down, left, and right. Furthermore, standard networks are extremely sensitive to position. If you train a simple network to recognize a face at the center of a photo and then move that face to the bottom corner, the network will likely fail. It doesn't understand that a nose is a nose regardless of where it appears in the frame. To solve this, we need a network that understands space. This is where the convolutional part of a CNN comes in. Instead of looking at the whole image at once, a CNN uses filters, also called kernels. Think of a filter as a small magnifying glass that slides across the image one small square at a time. As it slides, it performs a mathematical operation to look for specific patterns. Early layers in a CNN use filters to detect very simple things like vertical lines or horizontal edges. As we go deeper into the network, these filters begin to recognize more complex patterns. Layer 1 might find edges. Layer 2 might combine those edges to find shapes like circles or squares. Layer 3 might combine those shapes to identify a wheel or an eye. By sliding these filters across the entire image, the network achieves translation invariance, meaning it can recognize a pattern no matter where it's hiding in the photo. Processing every single pixel with dozens of filters is computationally expensive. It creates a massive amount of data. To keep the network efficient and robust, we use pooling layers. The most common version is max pooling. Imagine breaking your image into small grids and only keeping the most intense pixel from each grid. Pooling does two very important things. The first one is dimension reduction. It shrinks the image size, making the network faster and less power hungry. The second is robustness. It makes the network less sensitive to tiny distortions. As an example, if a cat's ear moves slightly to the left in a photo, the max value in that area stays roughly the same. Pooling helps the network focus on the presence of a feature rather than its exact pixel-perfect location. In a full convolutional neural network, we don't just use one filter or one pooling layer. We stack them together in a sophisticated pipeline. Think of it like a high-tech factory assembly line. At the start of the line, the network identifies raw edges and colors. As the data moves deeper, the factory assembles those edges into textures, then shapes, and finally complex objects. Each convolution layer extracts features, and each pooling layer simplifies those features so the network doesn't get overwhelmed by the unnecessary details. But how do we get a final answer like this is a cat? At the very end of this chain, we have a specialized map of high-level features. We finally flatten this 2D map into a long 1D list of numbers and feed it into a standard fully connected neural network, the kind we discussed at the very beginning of this series. This final stage acts as the decision maker, taking all the visual evidence gathered by the filters to make the final classification. This combination of spatial awareness and logical decision making is the secret behind the modern world. Facial recognition. Your phone doesn't just see pixels. It recognizes the specific spatial distance between your eyes and the curve of your jaw to unlock securely. Medical imaging. CNNs can scan thousands of X-rays, identifying the microscopic textures of tumors that might be invisible to the human eye, assisting doctors with superhuman precision. Self-driving cars. In real time, a car's onboard AI distinguishes between a solid pedestrian, a flat shadow on the road, and a cyclist moving at speed, all by identifying shapes and patterns in milliseconds. CNNs changed the trajectory of AI because they taught machines to perceive the world in 2D and 3D, recognizing objects with the same spatial intuition that we humans use every single day. We have come a long way in this journey together. We started with the foundation of the perceptron, the basic building block of every model. We learned the mechanics of backpropagation and how the chain rule allows a network to update its own weights. We explored the challenges of vanishing and exploding gradients, gave networks a sense of time and sequence with LSTMs, and finally, we have seen how CNNs use spatial filters to process visual information. Neural networks are no longer just black boxes. They are logical architectures built on calculus and linear algebra, designed to solve problems that traditional programming simply cannot touch. While the field of AI is moving at a rapid pace with models like transformers and generative AI evolving every day, the fundamentals you have learned in this series are the bedrock of it all. No matter how large or complex a model becomes, it is still built on these core principles of weight, activation functions, and gradient-based optimization. If you found this series helpful, please like, share, and subscribe to Mathemly. Your support allows us to continue creating clear, technical guides for the AI community. This concludes our series on neural networks, but it is only the beginning of your path in data science. You now have the technical foundation needed to explore more advanced architectures and start building your own models. Thanks for watching, keep building, and we will see you in the next series. If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.